All right. Good morning, everybody. So,
Morning.
first things first, like I said on Friday, some of you have decided not to do your 540 and STCW agreements that you have to sign. As promised, you're going to get points taken off if you haven't done that at this point. So, I would get that done before the next class, before you have more points taken off. Like I said, I'm not going to chase you. You have to do it. You're still going to be bound by this, even if you don't sign it. All right, this is a non-negotiable option. All right, take care of what you have to do and get it done. For the most of you, good job for doing it right away. Everybody else, get your crap together. Do it.
Professor, I have a question.
What's up?
I printed it out and signed it and converted it to a PDF. I was wondering if you got it.
If you submit it, I will see it, but I could check for you real quick. If there's a problem,
Thank you.
like say some people tried submitting it in other classes and it's submitted, but it came in basically as a jumbled text. I'm still counting that as a submitted. That's just the tech error. All right. So let's see. Let me find you real quick. Yeah, you're all good. I see one. So I'm assuming the other one should be fine too. All right.
All right, thank
So
you.
if it's there, you'll be set. All right. Everybody else, get your crap together. All right. Where the hell did my pen go? That's not good. I need that. There it is. It's in my pen drawer. All right. So as promised, we have a quiz today on piping. All right. Last 15 minutes of class. All right. So at 12:30, please give me a heads up if I go over. I don't want to take away time from you guys. All right. So let's see. We're going to go right into pumping today. All right. Is there any last minute questions on piping? We should have some extra time at the end, maybe 5 minutes or so, but anything before we go into something? Yes, no?
Questions?
What's up?
No questions.
No questions? All right. So one other thing before we go into actual pumps. All right. Lab starts Monday. Monday. All right. So 1:25, we begin in-person classes, right? Unless otherwise stated. So labs begin Monday. All right. If you have 540 lab, you have to start attending that. Remember, if you miss one, that's a failure for the entire class. All right. Don't miss these. They're actually very important. All right. There's a huge amount of information that gets pertained to crews and everything else along those lines. All right. You're going to be meeting at the gangway. All right. You're going to meet the 540 lab instructors, their first class cadets. All right. Here at Maritime, it's not going to be me teaching it. So you're going to get a different point of view. All right. Which is always a good thing. Now, some of you are going to be in a class. Pretty much everybody's going to have 4 instructors per class. All right. But some of you will not. Some of you will get a little lucky. Like Thursday at 9 in the morning, there's only 6 of you. So you're going to have 2 instructors. It's going to basically be a one-on-one instruction. All right. So you're going to be pretty good. You'll have 2 instructors there. And then Tuesday, you'll have 3 instructors. Thursday morning, you'll have 3 instructors. And then Tuesday, I said, but at 9 a.m. All right. Everybody else, you're pretty much going to be maxed out with full teachers. All right. So first class is going to be basically, you're going to be tracing out the engine room in a way that we're going to give you a piece of paper, and it's going to have like different pictures on it. And you'll be sitting there and you'll have like, okay, I'll label that as the LP turbine. And then you'll have the HP turbine right next to it. So you'll label that as the HP turbine. That's basically all you're doing on the first class, some safety stuff. All right. All that kind of good thing. All right. Now, what you'll need, you're going to need earplugs. All right. Highly recommend earplugs because The ship is in a working situation. All right. It's in full working, especially in the engine room. All right. So you're going to need earplugs. You're going to need gloves. It's always, especially now with it being in a working condition, gloves would be just good to have on you. You're not going to be really doing any sort of work, but it's just something good to have. All right. Things you will absolutely need is going to be pen, paper. All right. Something to write with, something to write on. All right. I recommend a clipboard because there's not a lot of spaces in the engine room to place a desk. All right. So if you don't want to make something as messy as possible, you need to basically have a clipboard, something hard to write on, something that's lightweight. That's why I recommend a clipboard. But if you have a different ability to do something else, that's your prerogative. Obviously, your boots, boiler suit, and you'll need a twit card. All right. So that way you can get on. Remember, you're going to meet at the gangway. All right. It's only a 50-minute class, so make sure you're there on time. If you are going to be meeting in a different spot, the next week your lab instructor will tell you. All right. Any questions on that?
We're meeting at the lecture time on Monday.
No, you're going to be meeting on your lab time. So it's going to be starting on Monday. So whenever you have physical lab on your schedule, 5:40 lab, you're going to be meeting at the gangway. It's not lecture.
Okay, thanks.
All right. Lecture, we're going to be meeting in person. All right, starting Monday. So make sure you are attending the classroom that we're assigned. All right, make sure you check that morning for the most up-to-date classroom. It might change that morning. All right. Now, because we're all getting COVID tested, right? Everyone's getting COVID tested. I believe last class told me yesterday and today, things like that. I need to know as soon as possible that you test positive. Okay. So that way we can have a contingency plan and I can make sure you guys get the knowledge and you also don't miss out on classroom time. Okay. Because if you have to quarantine for 2 weeks, all right, or however long they're going to quarantine you, well, let's say 2 weeks, that's 4 classes right there. All right. That's a lot of class time. And that will basically take us to the first exam. All right. These won't be posted via YouTube. I'm going to have to figure out something so that way you guys can still get your best education and everything like that. But I need to know going from here forward as soon as possible. I will get the emails, but it comes like super late. All right. I do get updated, but if it'll come faster from you. All right. So please, please, please keep me updated. All right. Tell me what section you're in. That will help out so much. All right. Just saying 540 or absent in this, in the subject line means nothing. All right. There's a lot of you and a lot of sections. All right. That being said, any questions on that or how we're going to deal with COVID or positive tests or anything like that? No, we're all good. Right, let me set this up. So we're going into pumps today. All right. Now, like I said, last 15 minutes of class, there is a quiz. There's no quiz coming up the next class. All right, we're not going to get through this whole thing. So quiz probably Wednesday, all right? And I will post this so that way you guys can use this right after class. Well, technically later this evening after the last class, all right?
That's next Wednesday or not next Wednesday?
It's going to be a week from today. There'll
Okay.
be probably a quiz on pumps.
Got it.
All right. Remember, every single time we finish a section is we're going to have a quiz the next class. All right. Guaranteed. Unless said otherwise. So pumps basics, before we get into that, pretty much we're going to be concentrating on centrifugal and positive displacement. All right. That is your 2 major pump types out there in the world. All right. So some terminology to begin with. All right, pumps deliver energy in foot pounds, pounds inch, joules, etc. Any unit of energy we can measure it in. All right, to a given volume. So volume is cubic inch, cc's, gallons, liters, everything like that. All right, something you can measure a volume in. So pressure is what we pretty much measure these things in. All right. So it's usually thought of as a force per area or force over area, but it's also an energy per volume. All right. So we measure this in a PSI type. All right. What we see here is what we're going to see through the rest of the class, which is a centrifugal pump symbol. All right. Now, the easier way to draw it, and what you will see is drawn specifically by me, is this. All right. But that's an industry standard as well. That's a centrifugal pump. All right. With right here being the suction and here being the discharge. All right. Same thing with the symbol here. This is our suction. This is our discharge. All right. That goes standard for centrifugal pumps. Don't worry. We'll be going over that when we go over the part of the pump in a second. Now, pressure times flow is power. All right. So we have energy over volume times volume over time. All right. So we get horsepower or watts. All right, again, I'm not going to be doing this to you with math. I don't think it's any point, but it's good to see. All right. This 1714 is just one of those great little things about our imperial units. All right. It's just added there. All right. It's the conversion number. It needs to be there. As you can see over here on SI, which is definitely superior, we don't have to worry about some random 1714 number. All right. It literally is pascals times meters cubed per second. All right. So horsepower is the same thing as watts. It's just they're different units. All right. So you could think of it as that. So we can see that we have this little cube here. Come on, do a little animation. There we go. As it gets inflicted energy onto it, it spits it out the other side. All right. We are inflicting an energy. All right. We're inflicting kinetic energy onto this. Now, we're going to talk about head. All right. Head is energy per pound of liquid, commonly expressed in feet, representing the vertical height of a static column of liquid, corresponding to the pressure of a fluid at the point in question. All right. In general, liquid may have three different types of energy. That is the capacity to do work, maybe due to these three factors. All right. So we have potential head. We have static pressure head. We have another one, but let's go over these two first. All right, so potential head is the energy of position, the work obtained in dropping a vertical distance. All right, so static pressure head is the energy per pound due to pressure. All right, so potential head is potential. It's like that potential energy. You're holding a glass of liquid higher in the air. This, as I bring it up higher or lower, has a different potential head. All right. Static is due to pressure. All right. So this would be considered static, and each different type of fluid has a different type of static pressure. All right. So we have water, gasoline, we have something called molasses. As we change its specific gravity and we change what type of material it is, we are going to change its height in static pressure. All right. Each one of these are at 1 PSI, but each one in a column of liquid is at a different height. That's our static pressure head. All right. And then we have velocity head, which is the kinetic energy per pound in the vertical distance a liquid would have to fall to acquire velocity. All right. So that would be that drop of water right there. All right. So what's the vertical distance that it would have to fall to acquire velocity? All right, utilizing that equation there. Again, don't care about the equation. You just have to know the difference in them. All right. Total pump head is the difference between the energy per pound on the discharge side versus the suction side of the pump expressed in feet. All right, so we're going to take the 2 points of measurement. All right, ZD is the distance in discharge. ZS is our distance in suction. We're going to go right through the middle, the datum plane, or basically the middle of the eye or the suction side of our pump. All right. Now, we're basically taking that distance and doing some math. We can figure out total pump head. I don't care about it, neither should you, unless you want to do marine engineering, but then you'll figure it out in those classes. All right. For this class, again, we just have to know our total pump head and understanding all of this. All right. Now we're talking about HF and HFS. All right. Those are friction losses. That's friction loss in piping. All right. Now, we were bringing a little bit of this up in valves where it has negligible effect on flow. All right. But why should we care about pipe loss? Why should we care about friction in a pipe? As an operator, as someone who is learning to operate a ship, why would this be important?
You have to overcome the friction loss by increasing your pressure.
So why would you, that's correct, but why wouldn't that be something that a designer would figure out? Why would it be necessary for you?
Because gravity is in effect all time.
Not just gravity, but the length of our pipes, right? We may be running into situations where the designer may not have thought that we would ever be in, right? I'll give you guys an example. And this isn't just something made up. This is something that as an engineer on a vessel, I had to deal with. All right. So we were in dry dock, all right, one time. And we were in a floating dry dock. All right. So we were above the water line. Now, our vessel was in the dry dock here. So we have in our engine room very sensitive electronics in this specific vessel that I was on. All right. It had to be air conditioned because of those electronics, not because we were in it. All right. They could hardly care less about the engineers. It was the fact that the computers in there would break if we didn't air condition them. And we couldn't turn them off because they were running specific pieces of equipment, even though we were in dry dock. All right. You really rarely go into full shutdown. All right. We weren't running our engines, but our electronics were still going. All right. Now, when we are in normal operating conditions, we cool our air conditioning with the seawater around us, right? Biggest, easiest thing in the world to cool anything to do with air conditioning, right? It's a giant heat sink. Well, being in dry dock, we had no access to the water around us. So what we had to do was we had to run a little garden hose in from the top. We used potable water, so our fresh water, from the top of the dry dock way down into the bottom of the engine room where we were at. All right. The designers thought of this and they made a hookup for our air conditioning to a garden hose hookup. But what was not thought of is the pressure loss of that garden hose. We used about 5-10 garden hoses to get from point A to point B. All right. So the only place we could see pressure was right here at position 1. All the way down here at position 3 in the engine room where it actually mattered. All right. It doesn't matter what the pressure at position 1 is. What matters is what the AC unit was going to be seeing at position 3, right? So the designers stated that our air conditioning unit could only take 60 PSI, let's say, because I don't remember the actual number. Well, we put at position 1, 60 PSI, because we didn't want to overload the system, right? We didn't want to break tubes. We didn't want to destroy our air conditioning system. So what happened was what? If we had 60 PSI at 1 and we were using 5 to 10 garden hoses, what do you think we were getting at spot 3?
Probably half or less.
Half or less. Yeah, we were getting basically a dribble. All right. So much so that it would actually trip off and we would lose our air conditioning system. We fought this for a couple of days, admittedly, the whole engine department. All right. Until we figured out that if we just put a damn pressure gauge at position 3 right before it went in, we would have figured out that it had like 10, 15 psi going in, which is not enough at all to run air conditioning. So we had to sit and we had to basically pump up the pressure at position 1 to about 120 psi in order to get 60 down at position 3. Because not only did we have a hose going into position 3, we couldn't just dribble it out like that. We had to get another garden hose to come up and go out. So that's where line loss becomes very important. Understanding that a pipe, the longer you have it, is going to be a serious problem. All right. If you don't think about your line loss, you could lose millions of dollars of electronics. All right. Just because you're not thinking about the pressure loss over a specific distance. And there's no manual to tell you this. All right. So that's why it's important to know these things. So pump types. We have kinetic, and then inside the kinetic type, we have what's called centrifugal. All right. Kinetic would be like throttling to valves, and a butterfly valve would be the centrifugal. All right. Centrifugal is the type, but is a kinetic function. All right. Just like a butterfly valve is a throttling valve, but the throttling valve part is the function. All right. So that's how you have to think about it. Inside kinetic, centrifugal exists in that category, as well as special effect. So those would be considered jet pumps. We're not really going to go into those, but you should know about them. So inside centrifugal, we have radial, we have axial, we have mixed flow. All right. Give me 1 second. There we go. So in centrifugal, this is inside a centrifugal pump. We have what's called as the impeller. That's all of these. All right. We have the eye, which is also our suction. All right. We have the volute. The volute is this whole area. All right. And then we have our discharge up here. Now, each one of these little lines here is called a vane, V-A-N-E. All right, it's the vane of the impeller. All right. So when this spins, all right, because this is a spinning pump, it's going to spin in this direction. All right, it's not going to be scooping water. It's flinging it. It's going to be imparting kinetic energy into it. All right. So the water or whatever fluid, let's just say water, whatever you're going to be pumping is going to be imparted kinetic energy into it with it flowing in that direction. All right. Remember, those veins aren't scooping. They're not scooping water up. They're imparting kinetic energy into it. All right. So the fluid comes out of the eye. It goes into the actual impeller. The veins inflict kinetic energy onto it, and that's how we're getting the fluid to be pumping. All right.
Excuse me?
Yep.
Is this what you added to the hose at the end, like if you had to build pressure?
No, this is actually what we did was we just increased the pressure. So our valve was like about like a quarter of the way open. So what we did was we pretty much opened it all the way. So we had a pressure gauge all the way up at the top of the dry dock. So we had a pressure gauge right there. And what we did was we disconnected the hose, and on our AC unit down in the little engine room down there, we basically rigged up another pressure gauge to see the actual pressure going in. So we didn't run any calculations. What we did was just added a pressure gauge, and we kept we kept opening the valve up at the top of the dry dock in order to increase the pressure. All right. And you'll see why we just didn't add a pump in line. One, it would be highly annoying. Two, we didn't have a pump to do it. And three, you'll see soon we'll have pump characteristics, why that really wouldn't work unless we had a full open valve here. All right. So we have different types. We have horizontal, or they could be vertical. All right. Again, we have our discharge up here, suction here in the middle. All right in that eye. Same thing here, suction, discharge. It's just a two different view. All right. And now we have our vertical down here. Now, this is not so easy to tell which side suction and discharge, right? We don't have a suction and discharge so easily shown. But what we can look for is our context clues. All right. We can see that over here, this dives down and goes into the center, right? So that must be our suction. But even if we can't see that, another thing that we can see is that the volute increases over here, right? It's increasing in that area. So that must be this side part of our volute. All right, so that's going to be our discharge. So using what's around us, using the ability to know what a pump, what a centrifugal pump looks like, we can determine what's going on. All right. Not every single ship you go out onto is going to have a nice little pipe with, an arrow going like this, like, Yellow Brick Road or what have you, being like, oh, this is lube oil. Follow me to the engine. That doesn't exist. You'd be lucky if you have tracings of the piping. All right. So impeller construction, we have closed impellers. All right. So we could see the vanes are basically hidden inside. All right. They have a physical barrier in between with a little gap. Those are the most common. All right. They have their own pros and cons, again, to the designer. We also have semi-closed and we have open. All right. So looking at these, we could tell that they have, you can see their vanes all the way through. They're not fully closed. And then we have this impeller over here. So as soon as the vane stops, the impeller stops. All right. It all depends on what you're looking for out of a pump. You're not going to take one of these and throw in one of those when your pump breaks. What you're going to go and do is there's going to be a data plate right here. You're going to type that number into your computer and it'll tell you the part number for your impeller. You'll order it and then hope to God that you get your correct impeller from the people who order it. And you don't get like toothpaste or something like that from the people ordering. All right. So that's how you're going to deal with these. Whatever you take out of whatever pump you're working on, you're going to put in the same exact thing. All right. You're not going to be changing the world here. So we also have single suction. All right. So where the suction's coming in via the eye. All right. It looks like it has two discharges, but in reality, it's not. Those two discharges are going to go to the same volute, right? And go to the same discharge line. All right. It just looks like there's two discharge, but in reality, remember, this is a circle. So it would probably, if it looks like that, we would have infinite discharges, correct? So remember that volute is there. We only have that one discharge. That is a great circle, and I know it. So now we have a double suction. Again, I'm not going to draw it, but it looks like our impeller has a double discharge, but it's not. All right. Same singular discharge, only has one volute to it. All right. But it does have a double suction. All right. Then we have also multi-stage, where it will come into the eye here, spit out, and then go right back into another eye. Again, it will spit out of the discharge and go into another eye, and just keep going on that till it goes and leaves. All right. So that's a multi-stage pump. All right. Any questions before we go into this chart?
The multi-stage, what does that do? Is that equalize for like better flow and like more equal pressure, or is that multiplying pressure?
So basically these things are going to have the same, we'll see in a second, but it'll have the same flow. All right, but it'll increase our pressure. We'll show you in a second with the chart. All right. Now, when you're studying this on your own, I will be referencing up to here, but make sure you pay attention to this. This gives a good visual representation of what's happening into the system, okay? So make sure you really look at that when you study on your own. Now, this is a pump chart. Whatever pump you get, you will get one of these pump charts. It comes in the manual. If you're going design, say if you're getting to marine engineering and you're going to be designing something, you will look at these pump charts and determine what you need to put in. Why do we learn about these? Well, if you're not a marine engineer, they're still useful. Just like when you learned earth science, where you had those reference tables, right? And they told you a stupid amount of information in those reference tables as long as you knew how to understand it, all right? This is the same thing. Knowing these charts will tell you so much information about these pumps that you just don't have to memorize. As long as you know how to determine, I'm not going to give you one of these on the test. I'm not going to give you a reference book. But as long as you know these charts inside and out, everything else you can determine from it about their characteristics if you're ever confused about it. All right. Now, we have something called our ideal line. All right. That ideal line is mathematically where we should be at. All right. But in actuality, we exist down here. All right. So this is what we're seeking. This is what our reality is taking us. All right. So the red line is our pump characteristic line. It is what we get. All right. So with our y-axis of pressure and our x-axis of flow, we are going to be sitting at whatever pressure is here. All right. And we will, as we get more and more flow, our pressure is going to fall off just a little bit. Now, we have a system characteristic. This is going to be calculated for whatever our pressure is, what our line loss is, all that information that we just went over, all that mathematics I said doesn't really matter, all right, that I don't physically care about in this class. These system characteristics is what's going to determine. You'll have these system characteristic lines, all right? So at this system, all right, we could see this pipe is, let's say, open 4 inches or whatever, all right? This system characteristic is for like a 4-inch pipe coming out. And it's not just the pipe. It could be going through heat exchangers. It could be going through, valves. It's the entire system in and of itself. But it's easiest to think that this is a 4-inch pipe right here. All right. So like anything else in the world, with engineering, we take one finger, we put it here, and we go straight up that way. I should change my color so we can see this, go purple. And take the other finger and we go that direction. And wherever they meet up, that's where they're going to physically be in this world. All right. We're not going to exist over here just because you want it to. If your system characteristic line is where it is right now, then that's where you exist. You don't get to pick and choose. All right. But we can manipulate this in different ways. All right. So if you look up in the top right, the system opened up. We now have a bigger pipe, right? We don't have as restrictive flow. Maybe we go from one type of valve that's more restrictive to another valve that's way more open. All right. We go from a butterfly valve, which has a little bit of restriction. We go to a gate valve, which has no restriction. That would be bad to change those two out, but still. All right. So let's say we go from a 4-inch pipe, and this is going to be an 8-inch pipe, way bigger. All right. Less restriction to flow. So we do gain from this point to this point, we gain a huge amount of flow, right? A lot more gallons per minute. But we lose just a slight bit of pressure. We're going to be going from about here to about like here, right? So it's not that much of a fall off, maybe 1 or 2 PSI but we'll gain probably like 20 gallons per minute. Right? And when we make this thing wide open, pretty much no restriction, our system characteristic is going to go way over to the right, again, following it to this spot. Let's call that a 12-inch piece of pipe. No restriction. And as you could see, we are going to have a higher and higher fallout. All right. So from where we were originally on that 4-inch, we went all the way down to our 12-inch pipe. So maybe we do have like a 5 PSI, 10 PSI difference. But we're going to gain maybe 80 gallons per minute of flow. All right. So if it's not so much of a specific pressure that you're after, what you're caring about is your flow. That's how you can change it and manipulate it, is your system characteristic. All right. So what if we go way back? We see at an 8-inch, again, follow the 2 lines. We go back even more. We go to that 4-inch pipe. It's more restrictive, less flow. All right. And even less, we go to a 2-inch piece of pipe. Now, we can also change out piping for openness. All right. We can also think about this as a valve, right? Where we could say a valve is 100% open. Let's say this one is 75% open. This one's 50. And this one's 25. All right. So you can even do this with a valve. All right. If that makes more sense to you. Now, if we go all the way here and we close it, we close that valve, or we have a restriction, we have a problem, a plug, what have you. We have a 0% open valve. We have shut off head. That's a no flow scenario. All right. No fluid is going to be moving. I'm going to erase that so you can see it easier. We exist in that spot. What is happening to the pump? Is our pump going to break? Is it going to do nothing? Look at our chart. Look what's happening here. We have pressure. But remember, we follow the 2 points. It just so happens that one hand is going to move straight up and the other is not going to move at all. All right. So we're not going to go super high in the pressure. This isn't going to happen. It's not like we're going to go to 2000 PSI just because we shut off a valve. All right. That's not going to happen. Our max is our ideal. We're also going to have no flow. All right. So what happens to this pump?
Burn
What
it up.
happens? Say again?
Would you burn it up since you have no flow, like lubricating it, or?
What do you mean by burning it up? You're
Well,
correct.
yeah, like I know on like pressure washers and stuff, when you run them without any water, like yeah, the pump's making PSI, but if you have no water in the pump, like you burn up the seals and everything.
Because you're not cooling it, right?
Yeah.
Okay. So that will happen eventually. All right. So you're right, but from not fully correct reasons. All right. Those types of pumps are not centrifugal pumps. Okay. So eventually you will burn up this pump. All right. Think about it. We're in a spot where we're not putting any more flow. We're not putting any gallons per minute. All right. It's a unit of volume. We're not having any more of that enter into the system. Even though our system is closed off, there's still an area. There's still an area before that valve. All right. So no more gallons per minute is going to be entering that area because we're at a zero flow scenario. All right. So if
are
you're
you asking what's going to happen to the pump if it stays running without a flow?
for 5 minutes, an hour, 2 hours, 2 days,
So it would overpressurize the system that's after the discharge of the pump, right? The discharge.
so
If it doesn't have an area to go into, then that portion of the system could overpressurize.
it won't overpressurize to breaking because it will only go to the height of its ideal. All right. So it still stays technically inside of its characteristics where it's built to be at. All right. So if we're not moving any more fluid into that area, whether from the discharge of that pump to the valve or wherever that obstruction is that's making this a no flow scenario, it could be 6 inches, 12 feet, doesn't matter. We're going to be adding no more fluid. All right. We're not going to be moving a liter, a gallon of water into there ever with it being at full no flow scenario, no matter what. All right. If we have a valve that's closed, no more flow, but we'll be maintaining our pressure. All right. Whatever this pressure is, we'll say it's like 60 PSI. It will just stay there and it's not going to harm the pump.
Question.
But if you keep it there for a couple days, you would harm the pump. All right. Because we're imparting kinetic energy into it. Right. And that energy has to go someplace. And what it will become, it will turn into heat energy. It will basically boil off any of the liquid that's in there. It will turn into a gas, become its own problems. All right. But this is actually how you start a centrifugal pump. You start with your discharge valve closed, and then you'll slowly open it to 100%. All right. So this won't damage the pump at all if you run it for 5 minutes, 10 minutes, an hour like this. I wouldn't run it for an hour, but 5-10 minutes won't damage the pump. All right. As long as it's filled with liquid, okay, you won't damage the pump. Now, like I said, this is just like that Earth Science chart. All right. Looking at this, you can determine a huge amount of information. All right. As long as you know where to look and how to read it. So if we're in a spot where we want to increase pressure, we don't want to worry about increasing flow, what would we do?
Piping size, diameter.
If we open up the piping size or if we open up the valve to a higher percentage open, we're not going to increase our pressure. Well, actually, our pressure will slowly decrease.
You cut it off.
Say again?
You decrease your openness, so your operating point.
So if we decrease,
Question?
yeah.
Well, what was your question again?
Oh,
What
okay.
are you asking?
If we want to increase our pressure, how do we increase the pressure to this pump?
I would say decrease the pipe size after the discharge point of the pump.
If we do that, we're going to get slight increases. All right. So
You
what if we
would
want to
decrease the flow?
Say again?
You would decrease the flow.
Decrease the flow. But what if we want a specific flow? All right. And remember, going from here to here may not be enough. Maybe we want to go from 60 to 120. Maybe we want to double it. I know that's not a good representation of it, but even going to 70. All right. Well, let's call that 50 because it's below. Even going to 70, or if we go to 50, how would we get up there? We wouldn't be able to achieve that at this point, right?
Would
You'd have to
maybe
change the pump.
in a row?
You'd have to change the pump. What else you got, Jerry? You said something.
I said kind of like before what we were talking about in one of the other lectures. You put two in series with each other. Would that
Two
work?
pumps right next to each other.
I mean, I don't think it would, but maybe that's what the answer you're looking for.
Yeah, so doing something like that, that would run them in parallel. But even if you run them in series after each other. All right, the other thing is changing out the pump. You could change out the pump, but there is an easier way. All right. Remember, this entire time we've been doing this, we've been messing with the system characteristic. We have not touched the pump characteristic. All right. And changing out the pump may not be an option. Okay. But if we run it at a different RPM, whether an increase RPM or a decrease RPM, we will get a drastic change in pressure. All right. So like I said, we'll have a slight difference. If we look here, if we don't change our system characteristic, we might have a slight change in our gallons per minute. Maybe we go from 50 to 55 gallons per minute, pretty much within tolerance of any sort of system out there. All right. But what we do achieve is maybe a greater pressure, something of a pressure that we want to be at. If we need to go from the basement, the lowest deck of our ship, and we need to go all the way to the top, all right, that pressure is what's going to push it up there, not the gallons per minute. All right. Gallons per minute is just going to be the rate of whatever tank we're filling is going to fill at. All right. So that's how we would do it. If we have a higher RPM, we can change our pump characteristic to increase our pressure. All right. And same thing if we decrease it, we will be able to decrease our RPM, we'll decrease our pressure. All right. So gallons per minute is based on the system. All right. How open the valve is, how much of restriction and flow we have. It all means the same thing. The system characteristic is based on its for the flow, and the pump characteristic is all based on the pressure, the RPM that we're running at.
So now, if the RPM increases, does the ideal also increase as well?
So it would increase to wherever it's running at. It would have its own ideal line, but honestly, you don't really pay attention to ideal lines. All right, that's just kind of stating that this is where, if you're going to call it a 60 PSI pump or what have you, that's where it's going to be. All right, just because you're sitting here at this position doesn't mean that you're not going to call this pump, let's say, a 60 PSI pump or something like that. All right, that's still going to be its designation because that's what it should be running. But in reality, honestly, it might be like 58, 57. It's not going to be a drastic difference. It's not going to be like 40 PSI. All right. And again, if you go down and you bring your RPM lower, you'll have a lower, you'll have a drastically lower flow all the way out here. But what you're really seeking after is your pressure. All right. Now, any questions on all of this before we continue? Remember, this shutoff head is okay. All right, it's a no flow scenario. Again, that's how you would start these pumps up. When we go into pump operations, we'll talk all about that. But just knowing that we're not going to have any fluid moving. We're just going to be imparting energy into it, represented by pressure. All right, but it's going to be at a constant pressure. All right, but nothing is going to be physically moving into that space. All right. So we're going to go into positive displacement. All right. Positive displacement is a reciprocating versus rotary. All right. So reciprocating is basically like anything that is shown here, like an engine would be considered a reciprocating positive displacement pump. All right. And then we have the rotary. All right. Which is basically whatever's spinning in this direction, this orientation. All right. And positive displacement is a fixed volume is going to move with each stroke. All right. It's not imparting energy. It's not a fixed pressure. All right. It's a fixed volume. No matter what this thing's going to be doing, the world could be crumbling around this reciprocating pump. And that pump, if it's going to be operating, will move a volume, a fixed volume, every single time it does one stroke, no matter what situation is happening. Okay? So before we get into this, knowing that it's a fixed volume, positive displacement pump will always move that fluid. All right. What in your home would be a positive displacement pump?
A sink.
So a sink would not be. That would actually just be based on head pressure for wherever you are. If you're in the city, it would be the water towers that are, on the top of the buildings. If you're in the suburbs, it would be a water tower in your neighborhood. If you're on a well, you have a completely different system, but it would still be based on pressure. Okay. What else?
Be a toilet.
Toilets use a siphon, same thing to fill it. You're thinking right that it is a fixed volume moving through it when it opens up, but it's not really would be considered that. But good guess. Troy, you were going to say something?
Well, just like fuel oil or something, don't you always want positive pressure? This way it never feeds back.
Remember, we're a fixed volume moving. All right.
Oh, okay.
What about
AC, air conditioning?
So air conditioning, yes. So the compressor on the air conditioning will be a fixed volume. Is that what you're thinking, or are you thinking the fan?
I'm thinking the air conditioning itself, because it's always going through the same fixed volume of pressure.
All right. So the compressor and we'll get into this later in the class, but a compressor will be taking in a fixed volume of refrigerant and discharging it every time. What's something even more simple than that? Something that an everyday item that we all use. Well, I hope we use it.
hand soap dispenser?
It's a hand soap dispenser. Were you in my last class, Nicholas?
No, I just thought of it just now.
All right, good job. So it's a hand soap dispenser. All right. It moves a fixed volume every single time. All right. Now, we'll get into more of it in a second, but think about one of those water guns, right? The ones that have they basically look like a giant syringe, right? You pull it open and that volume of water you suck in, right? And then you dispense it, and as you push it out, you get a volume of water squirting out to whoever you're trying to hit with that water, right?
A plunger is one.
Plunger, maybe, kind of, yes, no. It all depends on how it's being used. But
Would dishwasher be one?
a basic water gun would be a positive displacement pump. All right. So when you use a hand soap dispenser, all right, I have an eyeglass cleaner right here. All right. This is a positive displacement pump. All right. The shampoo bottles that have a square top is a positive displacement pump. Now, when you open one of these for the first time, right, you just came back from the supermarket and you have a brand new soap dispenser. What happens the first couple of times when you have to start it? What do you
Nothing
do?
Nothing comes out.
Nothing comes out, or it seems that nothing comes out, right? What is actually, in actuality, coming out of that?
Air.
Air.
Air. Yeah.
All right. That's our fluid that's going to be physically coming out of that pump. All right. So let me draw this so that way we can see it. Okay. Shoot, I messed up a little bit. Give me a second. Fix that. All right, and then we got the straw. All right, so, and that's whatever soap we have, okay? So every single time I spritz this, we have a volume of, even though it's aerosoled, it's still a physical volume of liquid that comes out of here. Man, it smells like alcohol. So when we do soap and we pump it up for the first time, we get air coming out of it. Right? So we are basically what's called priming our pump. This is a self-priming pump, right? Centrifugal pumps are not self-priming. So if you had a centrifugal pump in these things, you would have to prime these pumps. The entire world would probably crumble around stupid people not being able to self-prime a soap dispenser. We would never be able to fight coronavirus if soap dispensers were centrifugal pumps, because we can't even get people to wash their hands. Trying to teach them how to do that would be insane. Now, a positive displacement pump is self-priming for the physical reason that it moves a volume of liquid, a fluid, more specifically, every time it makes a stroke. So every single time you dispense, a physical fluid is moving through it, all right? A fixed volume. That fixed volume just so happens to be air those first couple of times, all right? So that first pump, you're there. The second one is there. Third one, fourth one, so on and so forth. All right, until you get whatever soap is in there that's dispensed. And then it stays there. You never have to prime again. All right. So this is a big understanding of self-priming. All right. You could take it and stick it into whatever you want, and it will prime itself, and then it will start pumping the fluid you want it to. All right. It is still pumping. It's pumping air, but we're talking about the fluid we want to pump. All right. Centrifugal pumps do not self-prime. Think about back to that chart, right? When we close off and we have a no-flow scenario, are we moving gallons per minute? No, we're not. We are stationary at a certain pressure, but we are not physically moving a gallon per minute. We're not physically moving a fixed volume. All right. So centrifugal pumps are not self-priming. They need to be filled with whatever fluid they're going to be sucking with, and all the way down to that suction pipe. All right. That being said, knowing the difference between these two will either have a chief engineer yelling at you and calling you some choice words because you swear you can't pump something because you can't prime it. Well, if you knew that the pump that you're going to be pumping a 55-gallon drum of oil is a positive displacement pump and it doesn't require priming, then you can get the job done without his interference, and he won't call you an idiot. All right? And knowing the difference between a centrifugal pump and being able to know how to prime it, which we will go over, and knowing how to prime it so that way you don't burn up your pump by having it what you think is running when it's really not. It's not moving any fluid. All right? Knowing the difference and how to tell and knowing why and what you can do will allow you to manipulate and change and go through our environment, which is what we are all trying to do as engineers. We don't like something, change it. Right? So if you have to pump a bilge way the hell on the other side of the ship, and the entire pipe is filled with nothing because it's a brand new ship, all right, you just have to turn on the positive displacement bilge pump that you have, because I guarantee you they all are. And you're going to be able to suck all that air out of that pipe and pump out that bilge. All right, because you know that eventually you will get that fluid, because you're just going to be moving just like a soap dispenser, that fluid closer and closer and closer, because your fixed volume of air is now moving and being dispensed. All right, the quiz is open. All right, before you start, is there any general questions on this? Because no matter what, you'll have the full 15 minutes, don't worry. Any questions on this before we go forward? No? Okay. All right, quiz is open. When you're done, you guys can leave. Keep it quiet